our fourth week for our aerospace meeting, we will be going over material selection. Afterwards, we'll have a Python assignment, and I will explain more of the details in the chat just because doing all that in one meeting may be a little overwhelming. So, whenever we're designing any type of spacecraft, we're ultimately trying to determine what materials and what type of materials we are expecting to implement in these systems. One of the most common materials that we use is aluminum alloys. The main use is for overall exterior frames, maybe boxes that store avionics, panels, brackets, though in practice, a lot of brackets are not aluminum and they're a lot stronger than aluminum. And then also we have other honeycomb like design patterns. The reason why is because aluminum is very, very cheap. It is very lightweight. You can make all sorts of geometries with it, so therefore it's very machinable. It is conductive and it is relatively, for its density, efficient for the amount of material we're applying of it throughout the spacecraft. Now, the biggest issue is that it is less suitable than a material like titanium, especially for high loads. Aluminum is one of the more softer metals, I would say. And okay, I did make a little uh, spelling error there, my mistake. But or no, sorry, no, that is anchor. But anyway, it is less suitable than very hard surfaces. Uh, but yeah, all interfaces that also experience very hot processes from equipment or environments should also be considered and tailored for that environment. There are many aluminum alloys available, so definitely do research on that. Next is titanium alloys. The main use, like I said, will be for anchor points, drill frames, high load joints, even brackets, as discussed earlier, maybe some propellant tanks or just tanks in general, and some level of fasteners. Titanium has been a very long standing and long proven material. It's been used in all sorts of applications. Now, why? It has a very high specific strength, toughness, it has relatively decent corrosion resistance. We often try for an alloy to incorporate some nickel in there as well because that additional material adds more corrosion resistance. And it's overall very acceptable for high load path performance measures, especially in simulations. Titanium is usually a good go to for a lot of general use cases. Now, big limitation, they are very expensive. Depending on the alloy, it can be difficult to machine. It is, as a metal, less conductive than aluminum, which, depending on the mission profile, may or may not have an impact. It just depends on how you plan to apply titanium to the spacecraft. Next, we have carbon fiber reinforced polymer. Also, we can just consider it carbon fiber. The main use is for equipment decks, antenna supports, and solar array backing. Also, it helps with the actual structure of instruments. So let's say, and it doesn't have to be necessarily instruments. I could make a cup holder and then put a camera through it and have that cup holder be made out of carbon fiber. Just as a random example, I just pulled out. Now, this is often used because it's very light, so it has low mass. So if there's ever an application or an opportunity where mass can be reduced on a spacecraft, this is typically one of the first materials that come to mind. Now, it's also widely considered for tight thermal expansion tolerances. This is also one reason why we often see more carbon fiber in automobiles nowadays. There are big limitations to it. It does require, as it is conductive, it requires grounding. It needs careful thermal design. Just because we have a material that is great at thermal resistance doesn't mean we can just put it anywhere. We still have to do our due diligence. Also bonding, so how we apply the carbon fiber to the craft in using what methods. So if we use an adhesive, if we duct tape it, all those have to be considered. And then also outgassing qualification. Just as a way to jog our memory from the last meeting, outgassing is whenever vapors in a vacuum environment separate from a solid. This is usually common in composites, and this, fits the use case. So outgassing qualification of having to essentially remove all the vapors from this before it gets assembled into the structure, and then continuous monitoring therefore until launch. Next
Which
is tungsten. Oh, yeah.
which one of the compounds had known issues with hydrogen embrittlement? Was that titanium?
Hydrogen embrittlement.
I think somebody wiped it down with alcohol one day and it structurally failed and they found out. I think it was titanium. I don't think it was aluminum.
I don't know. I'm more of,
I'm
if it is a
talking.
NASA related thing, I have no idea because I'm more on the
No,
defense
it was an
side.
airplane related thing about 40 to 45 years ago.
Oh,
Oh,
yeah, I'm not sure.
it was the high strength steel legs on the landing gear.
Oh, it was steel.
Must have been a special kind of steel, but I was wondering. I don't know. For some reason, I was thinking titanium, but it's so long ago. Anyway, go ahead. Go on. That's.
I imagine that it could also be titanium, just when dissolved hydrogen atoms they would um, bond to the metal and precipitate, thus becoming brittle. That is just something I'm just thinking of
Mhm.
randomly. Maybe I imagine all metals have something similar experience. Anyway, next,
Right.
tungsten
Yeah.
carbide. This is usually our main application for this will be drill bits. So think the actual mining equipment. So cutting teeth, pressure jaws, even abrasion liners. This is all very important. This is when we actually start to mine the asteroid. Now, why we choose this? Well, it's extremely hard and it's relatively wear resistant for regolith, all types of rocks, even metal rich deposits in the asteroid. Now, there's a big limitation, very similar to tungsten in general, is that compared to other materials, tungsten is very dense and it's very brittle. I know there's been application in recent times where companies are trying to use additive manufacturing, so 3D printing of refractory materials. A big issue when it comes to doing that is that a lot of these materials are relatively dense. Not necessarily tungsten, but it's just a general umbrella term for a lot of refractory alloys. It's very hard to implement 3D printing for these materials. We have the technology for a lot of it. The feasibility of actually doing it is very difficult. Now, these
They usually
let's
mean
use
the
as
economics are an issue too.
right, not just economics and then also performance as well. Comparing, for example, two welded parts of titanium will probably have different performance results in testing than 3D printed titanium. Just
Ah.
as a thought, just because of how it actually gets formed.
Hmm.
Uh,
Yeah.
but yeah, so these material, tungsten carbide, it's best used as a replaceable tip for inserts rather than a large continuous structure. So, for the sake of this mining operation, if we intend or hope to reuse this vehicle, which we should, uh, there's a lot of emphasis on renewable and reusable technologies. So that is a consideration if we're going to use a reusable technology, knowing how to inspect and then afterwards replace any mining equipment will be very, very important. But this is only applicable if it is reusable. If it's not reusable, oh well. Next, we have another use for cutting inserts and drills. It is polycrystalline diamond compact. Why? Well, because the cutting surface provides a very hard and wear resistant uh, properties, so it extends tool life, and it's very great when it comes to abrasive feedstock. So this is one mining material option that we can use. There is a limitation that it is brittle under impact and it is sensitive to poor mounting or excessive vibrations. Also, I believe as it is diamond, I forgot what type of material, but I believe it's something related to carbon. Something majority of carbon, I believe diamond has a hard time cutting through and actually wears a lot more. So understanding the material composition of what you're mining is huge because that it then impacts the mining equipment used and its materials. Next is silicon nitride ceramic. Typically, it would be used in bearing walls, anything that rolls essentially. I tried to find images of its application, but keep in mind a lot of good images for any of these are probably going to be proprietary to an extent. So open source images is what we try to aim for. Now, for this material, it is relatively hard and has a low density for a ceramic, which is great depending on our use case. It is relatively wear resistant. It is electrically insulating and very, very compatible in vacuum environments. One big issue though, very fracture sensitive. It requires a very detailed design with low tolerances, and vibrations will have a very big impact on the survivability of such. We'll slowly see when we evaluate vibrations throughout operation for this vehicle that vibrations have a very huge impact.
So that's actually making the material out of silicon nitride ceramic, right?
Correct. These are just
This is
random
what
materials.
this is what
I'm This presentation just lists out materials that are often used for missions similar to what we're planning. And so I'm just listing them out and explaining.
would any of them be used for as a coating material or as the main material?
Typically, I imagine for this material we're looking at, it would be homogeneous, so the entire material.
Right.
But there are some applications that could be used as a level of coating. A big consideration when it comes to coating is, of course, wear over time. Slowly but surely, coatings can char, coatings can melt, coatings can uh, suffer a large amount of abrasion. So a lot of considerations like that have to be considered.
Yeah, the
Next
silicon
is, yep.
that particular coating is fairly new compared to the 40, 50 years in the business that I was in daily.
Hmm.
That's got to be one of the newer ones.
Oh yeah, definitely. Our next will be borosilicate cover glass. Fun fact, they use this on the ISS for their solar arrays and some instruments like sensors, for example, as a small little cover. But the main use is essentially, as I described, a cover for equipment that is relatively sensitive or can even have failure if there is a level of destruction on it, whether it's from a very fine dust particle or very, very small meteorite. Now, limitations for this is that it's very brittle. Keep in mind it is glass. It is vulnerable to cracking, and overall it will experience dust abrasion, but ensuring the right thickness of glass, the right composition of glass, very crucial in order to allow it to be survivable in the conditions that it will be operating in. And it also it adds additional mass to instruments and arrays. Typically, whenever we measure instruments, we just measure them as is. We don't measure them with a coating of paint, which I mentioned paint specifically because paint gets very, very heavy when you apply that to a rocket or missile. Often we try to coat rocket bodies white as opposed to a darker color, just also because of uh, thermal issues as well. Anyway, moving on, we have Kevlar aramid fiber. This is great for providing a small shield for debris and small meteorites. And it is very flexible, so it does help absorb a lot of this energy when it does come into contact with the fiber itself. A very good pro to this is that it is lightweight, it is very high strength fiber. And like I said, it absorbs a lot of impact energy, very useful in any type of shielding system. It is limited to how the geometry of the frame it wraps around will be. It also won't survive a large collision. So ensuring that there are other systems to prevent space rock collisions is a crucial choice. And then also exposed UV energy on the surfaces could damage it. It just depends on the actual composition and what simulations and tests bring back. So very crucial to properly test for all conditions expected when implementing fibers. Fibers are relatively sensitive over time. They're great on the kinetics aspect, but more research has to be done. And in fact, there's a lot more research being done on these types of fibers, but a lot of that research is proprietary, and we'll probably won't have any idea until 10 or 20 years. Now, ideas and considerations that I just had in mind was when it comes to drilling something as rough as iridium, for example, I would say the best tools material would be the tungsten carbide, which is what I prefer, or the diamond compact cutting inserts. I would say the mining system, we should assume that it's obviously not pure iridium metal. We'll never find an asteroid of a pure specific material that's homogeneous throughout. So assuming that it's in trace amounts found naturally in space. I don't have the exact numbers of how the composition of a certain material is throughout generally, but that is one avenue to look through. And then also avoiding exposed polymers, especially in low Earth orbit. The oxygen there can erode exposed layers of the polymers, so ensuring that exterior frames is metal, or at the very least, having some level of protective coating. Next is to obviously increase shielding in identified vulnerable areas. These areas could include gas tanks that are close to the exterior frame, electronics whose payloads are also close to the frame. So ensuring we apply enough level of protection and definitely a multi-level layered series of protection. So maybe on the exterior we have Kevlar, and then one layer underneath that we have aluminum, and then a layer before that we have titanium. I'm just making something up here. Point being is increased shielding where there are more mission critical components. And then also plan for end of life wear for both mining equipment, storage, and overall frames. If this operation is going to be a continuous level of service, constant inspections and replacements will be needed. If not, and it's a one time operation, not so much. Usually, regardless of the operation, there's always inspections being done. Um, yeah, this opens up the concept for reusable drills, which is what I mentioned for the tungsten carbide, and also liners as well. Now, that is about it. That what I have for today. Let's see the
Ah, Agent Orange
chats if we have
arrived.
anything.